A 40-story rocket falls back from space at over 1,000 miles per hour, and a pair of steel arms reaches out and catches it. No parachute, no ocean splashdown, no human hand on any control. The only reason this works is because no human being could ever react fast enough to make it happen.
This is the first and only orbital-class rocket booster to land and be reused.
Think about what that actually means for a moment. You have a vehicle that weighs over 200 tons fully loaded. It has just fired its engines in space, flipped around, and is now falling back through the atmosphere faster than a bullet. The margin for error is measured not in seconds, but in milliseconds. And somewhere inside that rocket, an AI is making thousands of decisions every single second, adjusting thrust, correcting angle, calculating the exact moment to deploy the grid fins, computing the precise instant those catch arms need to close. If the AI is off by even a fraction, the rocket misses. Or worse, this is not a stunt. This is not a publicity move. This is the most consequential engineering challenge in the history of spaceflight. And the fact that it has been solved changes everything about how humanity gets to space. To understand why, you need to understand what came before. For the first 50 years of the space age, rockets were expendable. You built them, you launched them, you never saw them again. Every single mission meant building a brand new vehicle from scratch. It was like flying from New York to London, and then throwing the plane into the ocean when you landed. The cost was staggering. A single launch could run $150 million or more. And because each launch was so expensive, space stayed locked behind government budgets and geopolitical ambition. Nobody could afford to go often. Nobody could afford to fail. Then everything started to change. In 2015, SpaceX did something that drew gasps from engineers around the world. A Falcon 9 first-stage booster came back from the edge of space and landed on its own legs, upright, on a concrete pad, under its own power. It sounds simple. It was not. It required solving a guidance problem that had stumped aerospace engineers for decades. The booster had to reignite its engines at exactly the right moment, pitch to exactly the right angle, deploy landing legs at exactly the right altitude. But Falcon 9 landing was just the beginning. What SpaceX is doing with Starship makes a Falcon 9 landing look like parking a bicycle. Starship is a different category of machine entirely. The full Starship system stands 123 meters tall, taller than the Statue of Liberty with its pedestal. It is the largest rocket ever built, the most powerful rocket ever built. And unlike any rocket before it, the entire system is designed to be reusable. Not just the first stage, everything. The first stage is called the Super Heavy Booster. It carries 33 Raptor engines, 33. When they all fire together, they produce around 16 million pounds of thrust. Nothing in history has come close. When a Starship mission is complete, Super Heavy doesn't land on legs like Falcon 9. It gets caught by a mechanical arm system at the launch tower, nicknamed Mechazilla. This is where the AI problem gets extraordinary. Imagine trying to thread a needle, but the needle is falling at 150 miles per hour, and it weighs as much as a loaded jumbo jet, and you have less than 2 seconds to close the arms at the right moment. The catch window is vanishingly small. The booster must arrive at a specific position in space, at a specific velocity, within a tolerance that is measured in centimeters, not meters, centimeters. No human operator can watch a camera feed and press a button in time. The biological limit of human reaction time is around 200 milliseconds. The catch window is far tighter than that. So the decision doesn't belong to a human, it belongs to the AI. The flight control system running Starship's descent is what engineers call a closed-loop guidance algorithm. It is constantly ingesting data from hundreds of sensors: accelerometers, gyroscopes, GPS, radar, altimeters, camera-based optical flow sensors. Every few milliseconds, the system runs a predictive model. It asks, given where I am right now and where I am heading, what do I need to do in the next tenth of a second to end up exactly where I need to be? Then it acts. It throttles individual engines, it tilts the grid fins, it adjusts the engine gimbal angles to steer through the air, and it is doing this continuously, all the way down until the moment the arms close. But there's a deeper layer to this than just reaction speed. The AI isn't just reacting, it is predicting. Before the booster even re-enters the atmosphere, the system is running models of how the descent will go. It is accounting for wind shear, temperature gradients, small variations in fuel load that change the vehicle's center of mass. The version 3 Starship, the latest iteration, brought significant upgrades to this system, improved Raptor 3 engines with higher thrust-to-weight ratios, structural changes that reduced vehicle mass while increasing propellant capacity, and critically, updated flight software that incorporates lessons from every previous test flight. Each test generates terabytes of telemetry data. Every anomaly, every unexpected vibration, every deviation from the predicted flight path, that data feeds back into the model. The AI gets smarter with every launch. If this is blowing your mind, hit subscribe. We cover science and technology at this level every single week, and you won't want to miss what's coming next. Here is what makes the catch maneuvers so remarkable from an engineering standpoint. The system has to make a go/no-go decision autonomously. If the booster is slightly off trajectory on approach, the AI has to decide whether to attempt the catch or wave it off and send the booster to a water landing. That decision has to happen with no human in the loop. There is simply not enough time. The AI assesses the approach trajectory, computes the probability of a successful catch within the required tolerance, and either commits or aborts. Engineers describe this as one of the hardest autonomy problems in aerospace. You need a system that is aggressive enough to attempt the catch when conditions are marginal, but conservative enough to recognize when the risk is too high. Getting that balance wrong in either direction has consequences. Too conservative and you waste the booster, too aggressive and you destroy the launch tower. The fact that this system exists at all, let alone that it works, is a testament to what modern AI-driven engineering can achieve. Right now, the most cost-effective rocket in the world is Falcon 9. A Falcon 9 launch costs around $70 million. That seems cheap compared to older rockets. It is not cheap in absolute terms. That is still $70 million to put a few tons of cargo in orbit. Starship, at full reusability, changes the maths completely. SpaceX has stated a target of under $10 million per Starship launch. Some internal estimates have gone even lower. The goal is eventually under $1 million per flight. How? Because if you catch the booster, and you refurbish it, and you fly it again within hours or days, the amortized cost of the vehicle collapses. The fuel to get to orbit costs a few $100,000. The engineering and manufacturing cost of the vehicle gets spread across hundreds of flights. It is the difference between a commercial airliner and a single-use private jet. The airliner looks more expensive to build, but because it flies 20,000 times over its life, the cost per journey is a fraction of the alternative. This is why the AI matters. Full reusability is only possible if the vehicle can be caught and turned around quickly, and that is only possible if the AI can bring it home precisely enough, consistently enough, that no major repairs are needed between flights. If the booster lands on legs and tips over, you have a disaster. If it misses the catch and lands in the ocean, you have saltwater corrosion and weeks of refurbishment. But if the arms close at exactly the right moment, and the booster is mechanically intact, you could theoretically refuel it and launch again. That is the endgame. That is what every test flight is working toward. And the implications go far beyond the economics of satellite launch. Mars. That is the destination SpaceX has been building towards since the beginning. A single Starship can carry up to 100 tons to orbit. With orbital refueling, another process that requires extraordinary autonomous docking AI, a fully loaded Starship can reach the Martian surface. That is more cargo capacity than anything ever sent to another planet, by orders of magnitude. But none of it works without the catch, without the rapid reusability, without the AI that makes it all possible. The engineers at SpaceX have built something that older aerospace thinking said was impossible. You cannot catch a booster. The tolerances are too tight, the dynamics too complex, the risk too high. They were wrong. And the reason they were wrong is that they were imagining a human operator at the controls. Once you take the human out of the loop and replace the reaction time bottleneck with a machine that processes sensor data 1,000 times faster than any human nervous system, the impossible becomes achievable. This is the pattern you see again and again at the frontier of engineering. The bottleneck is not the hardware, it is not the fuel, it is not the physics. The bottleneck is always human limits. And when AI removes those limits, things that looked impossible start happening in the real world. If you want to keep following stories like this one, subscribe. We post every week.